At this very moment, you are tearing through space at more than 1.9 million miles per hour. You feel absolutely nothing. That stillness is a deception. Earth does not simply orbit. It spirals, plunges, and gets hauled toward something so enormous that humanity spent 3 decades searching in the wrong direction. Behind us, a billion light-year void shoves us forward. Ahead, a supercluster containing tens of thousands of galaxies exerts an even greater pull. And, buried within a fossilized pressure wave from the Big Bang, lies a ring that has no right to exist. We will explore the hidden attractor, the void that propels us, and the fate the universe may have already sealed. If you want to follow where this leads, subscribe. We begin this instant. You cannot perceive it. The floor under your feet feels firm and motionless. The air round you holds its position. Your hands stay wherever you place them. Every sensation tells the same quiet lie. You are standing still. The ground beneath you is traveling at more than 1,000 miles per hour. At the equator, Earth's surface spins at roughly 1,040 miles per hour. That exceeds the cruising speed of most commercial jets. Fast enough to sweep you around the planet's entire circumference in just under a single day without ever stepping off the surface. Fast enough that if you could somehow float free of the planet and watch from a stationary point in space, you would see the surface blurring below you. And yet, standing on that spinning surface, you feel nothing whatsoever. No rushing wind, no vibration underfoot, no sideways pressure against your body. Just perfect calm. The reason for this is exact, and it matters for everything that follows. When every component of a system travels at the same speed in the same direction, none of those components can detect the motion from within. The air, the ground, your seat, your body are all spinning together at the same rate. Physics gives this a name. It is called an inertial frame. A traveler seated inside a smoothly cruising aircraft at altitude feels no sense of speed because nothing inside the cabin is shifting relative to anything else. Motion only registers in your senses when something in your surroundings is accelerating or changing direction relative to you. On a rotating planet, that contrast never arises. The entire world turns alongside you, and so the spin remains invisible. This is where the strangeness starts to accumulate. Earth does not only spin, it also travels through space around our star. The solar system itself moves through the spiral arms of the galaxy at speeds that make Earth's rotation seem trivial. And the galaxy is being pulled through something grander still, aimed at a destination that took the full span of modern science to even begin identifying. These layers of motion do not cancel one another out. They compound. Each one sits on top of the last. Each one is swifter, stranger, and more difficult to account for than the one beneath it. This story is the complete reckoning of all those layers. Some of what scientists discovered along the way was elegant and satisfying. Measurements held up, velocities matched what theory predicted, the equations cooperated. But other layers demolished decades of carefully built understanding. One major discovery turned out to be catastrophically mistaken within 20 years. Another showed that the structure believed to be the primary force steering us through space accounted for less than half the real explanation. And the deepest layer of all remains contested today, its implications so extreme that even the researchers who produced the evidence are still arguing over what it means. Each stage of this story adds another layer to the picture. Each one makes the previous look modest. The rotation is where we begin. 1,000 miles per hour. imperceptible to every human being who has ever stood on this surface. A staggering velocity that registers in the body as total calm. It gives us the rhythm of day and night. It shaped every culture that ever structured itself around a calendar. It is the motion most deeply woven into human experience. And in the full accounting of Earth's actual speed through the cosmos, it is almost irrelevant. The total velocity confirmed by direct measurement against the oldest radiation in the universe exceeds 1.9 million miles per hour. The destination that all of this speed points toward took scientists until the end of the 20th century to begin mapping, and they are still revising that map today. We start at the slowest point. This will be the most leisurely we ever move in this entire story. For most of human history, the notion that Earth moved at all was treated as absurd. The ground felt permanent and anchored. The sky wheeled overhead in orderly arcs. Every observation of everyday life pointed toward a stationary Earth and a cosmos in motion around it. It took centuries of astronomy, philosophy, and disputed mathematics to demonstrate the opposite. And even then, the motion was something to be debated in manuscripts rather than experienced in the body. The facts, once properly established, are staggering. Earth circles our star at approximately 67,000 miles per hour. That is equivalent to crossing the continental United States from coast to coast in about 3 minutes. In a single day, Earth covers more than 1.5 million miles along its orbital track. Over the course of a year, it sweeps through nearly 600 million miles, returning to almost exactly its starting position and doing so with such smoothness that the entire journey is undetectable. The quietness of that voyage is what makes it so disorienting to contemplate. There is no atmosphere in space to press against the planet, no friction, no medium, no resistance of any description. The planet moves through near-perfect vacuum, and vacuum offers no sensory information. On the surface of a world, speed makes itself known through wind, through the trembling of the ground, through the compression of air. Eliminate all of that and speed becomes invisible. The most extreme velocities in our corner of the galaxy pass without leaving any trace on the creatures carried along inside them. That invisibility is precisely why the heliocentric picture of the solar system was so hard to establish. The correct understanding that Earth orbits our star rather than the reverse was proposed in antiquity and suppressed, then revived and contested again across generations. The obstacle was not simply institutional resistance. It was genuinely baffling to explain how a world in rapid motion could feel indistinguishable from a stationary one. That puzzle has a real answer rooted in the same inertial frame that explains the imperceptibility of the spin. But arriving at it required a wholesale reimagining of what motion actually means. Here is something worth pausing on. Earth has been moving at 67,000 miles per hour without interruption for 4.5 billion years. That motion has never meaningfully slowed, varied, or stopped. Every person who has ever drawn breath, every civilization that built and collapsed, every species that walked or swam or crawled across this surface did so while the ground beneath them was already deep into a journey older than life itself. The journey began hundreds of millions of years before the first living cell appeared. And this orbital motion, immense and ancient as it is, does not explain our full velocity. The solar system and the star it orbits are not fixed in space. They are themselves in motion through something much larger, carried along by forces that make the simple mechanics of one planet circling one star seem like a footnote. The 600 million miles Earth traces each year is a tiny arc within a far grander trajectory, one that takes the solar system on a journey no human lifespan could meaningfully encompass. When the early astronomers concluded that Earth orbits our star, they believed they had arrived at the real answer, the bedrock truth about our motion. It was a brilliant achievement that reorganized all of science. It was the second layer of a much deeper structure. What lies above it makes 67,000 miles per hour look like the prelude to a storm. Picture a clock so vast that 1 second on its face equals 1,000 human lifetimes. Picture one complete rotation requiring so long that the last time its hand occupied its current position, reptiles were only just beginning to establish their dominance over land. That is approximately the scale of the orbit you are presently completing. Our solar system circles the core of the Milky Way at close to 500,000 miles per hour. That figure is confirmed through multiple independent lines of measurement. The orbital speed varies modestly depending on the method employed, but converges in the range of 496,000 to 560,000 miles per hour, roughly 220 to 250 kilometers per second. By any comparison drawn from ordinary human experience, that speed exceeds comprehension. And yet the orbit is so vast that even at that velocity, a single complete circuit takes between 220 and 250 million years. Astronomers have a name for this unit. One orbit of the solar system around the galactic center is called a cosmic year, or, alternatively, a galactic year. The last time Earth occupied its current position within the galaxy, the Triassic period had not yet opened. The first true dinosaurs were only beginning to appear on a planet whose land masses bore no resemblance to today's. Before that orbit, there were no dinosaurs of any kind. Before the orbit prior to that, there were no terrestrial vertebrates at all. Count back 20 of these orbits, and you reach the formation of Earth itself. That is the full tally of cosmic years our planet has accumulated in its entire existence. 20. 20 complete circuits around the galaxy. That is the whole history of this world. Consider what that implies about scale. The Milky Way is so enormous, and the orbital path so colossal, that even a planet as ancient as Earth has barely sampled the galaxy it inhabits. And our galaxy is just one of hundreds of billions. Here is where this chapter must begin building toward something larger, because 500,000 miles per hour, the speed of our galactic orbit, confirmed and measured and printed in textbooks, is itself only one layer. The solar system is not merely drifting in a quiet arc around the galaxy's edge. The entire galaxy, and everything gravitationally tied to it, is moving together in a specific direction at a speed that, added to everything else, produces a combined velocity that no one in the history of science suspected until relatively recently. The Milky Way occupies one of the galaxy's minor spiral arms, positioned roughly midway between the galactic center and the outer rim. Our location is neither central nor extreme. We are mid-orbit in a structure containing at least 200 billion stars, every one of them also orbiting, every one also in motion. The stellar neighborhood around us evolves over cosmic time. Stars that are near neighbors today will be separated by vast distances in 10 million years. The constellations that define our current sky will be unrecognizable after another galactic year. By the time the final layer is added to this picture, the comfortable orbital arc you are currently completing around the galactic center will feel almost unhurried. To grasp what comes next, you need to understand how scientists first realized something was wrong. It was not a dramatic telescopic discovery. There was no obvious signal. It was a subtle pattern buried in numbers that had no business being there. And the 7 astronomers who found it had no sense at the time of how far the mystery extended. All they knew was that galaxies were moving in a way that defied explanation. Something had to be pulling them. In the mid-1980s, 7 astronomers began assembling data that simply did not fit any accepted model. They were studying elliptical galaxies, measuring distances, through a technique called the fundamental plane method, which connects the size and luminosity of a galaxy to its internal velocity dispersion. It was demanding, precise work, and the results kept coming back wrong. The group gave themselves a name. They called themselves the 7 Samurai, a title that reflected both the size of the team and perhaps the sense that they were contending with something vast and unresolved. The members were David Burstein, Roger Davies, Alan Dressler, Sandra Faber, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner. Their combined work, published formally in 1987, documented something extraordinary. Across an enormous arc of sky, galaxies were moving hundreds of kilometers per second faster than the standard model of cosmic expansion predicted. To understand why this alarmed the scientific community, you need to understand what peculiar velocity means. When astronomers calculate how quickly a galaxy is moving away from us, they expect a number governed by Hubble's law. In a uniformly expanding universe, every galaxy recedes at a rate proportional to its distance. The farther away it sits, the faster it retreats. But occasionally, a galaxy moves at a speed slightly different from that prediction. That difference, that deviation from the rate cosmic expansion alone would produce, is called peculiar velocity. It indicates that something in the local environment is exerting an extra gravitational tug on the galaxy, accelerating or decelerating it beyond what pure expansion would generate. What the 7 Samurai uncovered was not a gentle nudge. It was a systematic, coherent drift spread across thousands of galaxies spanning an immense region of sky. All of them streaming in the same direction, all exhibiting the same deviation. The pattern was too organized, too large, and too consistent to be noise. Something was drawing them all inward. The direction of that pull pointed toward a region associated with the constellation Centaurus. The galaxies were not merely receding from one another, the way a smoothly expanding universe would produce. They were also sliding sideways, converging on a single location in the sky. That location corresponded to a region of extraordinary mass, a concentration so extreme that it was accelerating everything in the surrounding neighborhood toward it. Alan Dressler supplied the name. He later explained that the object deserved something more evocative than a clinical label like New Supergalactic Center or Very Massive Object. The name he settled on was simple, accurate, and faintly ominous. He called it the Great Attractor. The name took hold because it described the thing precisely. Something out there was attracting matter on a cosmic scale. Galaxies, hundreds of millions of light-years away, were being drawn toward a single concentration. Our own galaxy was among them. Our solar system, our planet, every person and every object on it had been moving toward the great attractor for billions of years, and would continue doing so indefinitely. The obvious next question was what exactly it was. That question turned out to have a deeply frustrating answer, because the great attractor sat in precisely the wrong part of the sky. there is roughly 1/4 of the celestial sphere that optical telescopes simply cannot see. It is not dark, it is not empty. It is in fact among the most brilliant regions of the night sky, dense with stars, glowing nebulae, and thick veins of interstellar dust. That very brightness is what creates the obstacle. The disk of our own galaxy cuts through the middle of this region like a river of fire, and everything behind it is obscured. Light from distant galaxies passing through this band is absorbed, scattered, and overwhelmed by foreground radiation. Billions of our own stars lie between us and the objects we need to study, making them effectively undetectable. Astronomers call this the zone of avoidance. It accounts for roughly 1/4 of the entire sky. Any survey of the universe dependent on visible light carries a permanent gap in this region, like attempting to map a continent with 1/4 of your chart simply torn away. Through most of the history of modern astronomy, this gap was accepted as an unfortunate but fixed limitation. You worked around it. You filled in what you could and left the rest blank. The problem with the Great Attractor was that it sat almost directly behind this zone. The mass concentration responsible for pulling our galaxy, our neighborhood, and hundreds of thousands of other galaxies through space was hidden behind the single most impenetrable region of sky available to observation. The irony did not escape the scientists trying to investigate it. They had traced its gravitational fingerprint in the motions of galaxies on both sides of the zone. They could perceive its influence the way one can detect a current in a river without seeing the water moving beneath the surface. But direct observation was impossible. The veil held. To pierce the zone of avoidance, astronomers had to abandon visible light entirely. Radio waves travel through interstellar dust with far less interference than optical photons. Infrared light is similarly more penetrating. X-rays generated by the superheated gas inside massive galaxy clusters can cut through even dense sections of the galactic plane with acceptable clarity. In the years following the Seven Samurais announcement, teams of astronomers worked systematically across all of these wavelengths, attempting to chart what lay behind the obstruction, trying at last to see the object that was pulling them. The resulting picture did not arrive cleanly. Different surveys returned different conclusions. Different mass estimates gave wildly divergent figures. Determining the identity of the core structure behind the Great Attractor, the specific object at its gravitational center, required years of effort. When it was finally resolved through X-ray observations, the result commanded genuine respect. Thousands of galaxies locked in each other's gravitational grip. Collisions unfolding on a scale that made ordinary description inadequate. Energy output registered across the entire electromagnetic spectrum. But even as this identification was being celebrated, the underlying numbers were already quietly wrong. The mass estimates had drifted off target, and the scale of that error would not come fully into focus for another decade. What researchers believed they had discovered, what the early data appeared to confirm, was about to reveal itself as a partial answer at best. When the complete picture finally arrived, it required rewriting almost everything published in the 2 decades since the Seven Samurais' original paper. The decisive advance came from orbit. The Röntgen satellite, launched in 1990 and known as ROSAT, was built to survey the sky in X-ray wavelengths. Hot gas trapped in the gravitational wells of massive galaxy clusters radiates intensely in X-rays, and X-ray light penetrates the dust and gas of the galactic plane far more effectively than optical wavelengths. It was not a perfect solution to the zone of avoidance problem, but it offered a genuine opening. In the early 1990s, X-ray observations from ROSAT revealed the dominant structure lurking behind the Great Attractor Zone. It was a galaxy cluster cataloged as Abel 3627, but better known by the name of the constellation toward which it lies, the Norma Cluster. What the data revealed was impressive by any measure. The Norma Cluster packs thousands of galaxies into a volume of space too small to comfortably contain them. Many of those galaxies are in the process of colliding, caught in the slow gravitational crush of neighbors too massive to escape. The collisions generate enormous volumes of radio emission. The hot gas permeating the cluster blazes in X-rays. The entire structure is a churning, radiating knot of matter locked in a gravitational embrace that has been tightening for billions of years. It had mass, and it had it in abundance. Early calculations produced a figure that appeared to vindicate everything the Seven Samurai had measured. Initial estimates placed the total mass of the Great Attractor region, with the Norma Cluster at its core, at roughly 10,000 times the mass of our neighboring Andromeda galaxy. Andromeda is a system of approximately 1 trillion stars. 10,000 times that figure approaches the limits of useful human visualization. If those estimates were correct, the Great Attractor stood among the most massive concentrations of matter in the local universe, and its gravitational reach over everything in the neighborhood, including the Milky Way, was fully consistent with the peculiar velocities the Seven Samurai had documented. For approximately a decade, this was the accepted picture. The Great Attractor had been located, its mass estimated, its identity confirmed. The anomaly in galactic motion had an explanation. The case seemed effectively closed, except the numbers were wrong. Not marginally wrong, not off by some small percentage requiring minor correction. The mass estimates would eventually be revised downward by a factor of 10. The object identified as the primary engine of our galaxy's motion across space would turn out to account for less than half of that motion. And the true dominant attractor, the structure genuinely responsible for the largest portion of our trajectory through the cosmos, was not in the Great Attractor Zone at all. It was 4 times farther away, in a different part of the sky entirely, and it had been noticed decades earlier by a different astronomer. That astronomer had no idea what he was looking at in 1930. Neither would anyone else for another 70 years. Science does not always correct itself on a human timescale. The mass estimates for the Great Attractor were accepted, published, cited, and built upon for roughly 2 decades. Research teams used those numbers as the foundation for models of galaxy flow throughout the local universe. Papers tracing peculiar velocities, charting the gravitational landscape, and mapping our cosmic trajectory all rested on figures that were, as it would turn out, dramatically inflated. The correction arrived in 2005 from a survey called the Clusters in the Zone of Avoidance Project. This X-ray survey, designed specifically to chart galaxy clusters concealed behind the galactic plane, produced revised measurements of the Norma Cluster and the region around it. The new numbers were striking. The Great Attractor region had only about 1/10 the mass originally calculated. Not 1/10 of a few percent less. 1/10. The early estimates had been inflated by a factor of 10. The explanation was a statistical distortion known as the Malmquist bias. Understanding the Malmquist bias requires grasping one particular problem inherent to large-scale cosmic surveys. When you search the sky for galaxy clusters, the clusters you successfully detect are the brightest and most luminous. Clusters that are dimmer, less massive, and therefore harder to observe go systematically undercounted. The survey does not capture a balanced sample of what is actually out there. It captures a sample skewed heavily toward the largest and most conspicuous objects. When you then calculate the mass of a region using only the clusters your instruments can detect, you are consistently inflating the estimate by missing all the smaller contributors. The early mass figures for the Great Attractor had suffered exactly this distortion. The Norma cluster and its immediate neighbors were real, confirmed, and genuinely massive. But the surrounding territory was nowhere near as densely packed with matter as the initial calculations had assumed. Correct for the Malmquist bias and the number collapses. Here is the consequence that mattered most. The peculiar velocity of our galaxy, the speed at which the Milky Way is moving toward the Great Attractor Zone above and beyond simple cosmic expansion, requires a specific quantity of gravitational pull to explain it. The revised mass of the Great Attractor could account for only approximately 44% of that velocity. The remaining 56% needed a source. Something else was contributing to the pull. Something larger, something farther away. Something that 3 decades of research focused on the Great Attractor had not adequately addressed. The cosmic puzzle the Seven Samurai had uncovered in the 1980s had not been solved. It had been partially explained by a structure that turned out to be a supporting character in a story with a much more imposing lead. That lead had been sitting in plain sight since 1930. Harlow Shapley had noticed something remarkable in that part of the sky nearly a century earlier. He described it as a cloud of galaxies, which was considerable understatement. What he had found was the most massive accumulation of galaxies in the local universe, and almost nobody had taken it seriously enough as the dominant attractor. That was about to change. Harlow Shapley was one of the most consequential astronomers of the 20th century. He was the scientist who correctly located our solar system in the outer regions of the Milky Way, dismantling the assumption that we occupied a privileged position near the galaxy's center. His work permanently altered how humanity understood its own place in the cosmos. In 1930, in the course of his broader sky surveys, Shapley noticed something in the direction of the constellation Centaurus, a concentration of galaxies that appeared unusually dense, more tightly packed than the surrounding sky. A region where the count of galactic objects was markedly above the average. He noted it. He published it. And for decades, the astronomical community largely filed it away as an interesting data point without pursuing its full implications. The Shapley concentration, as it came to be called, lies approximately 650 million light-years from the Milky Way. To put that in perspective, the Great Attractor sits roughly 200 to 250 million light-years away. The Shapley concentration is more than 4 times farther. At that distance, in the middle decades of the 20th century, measuring its mass and gravitational influence with any precision was simply beyond the reach of available instruments. The necessary surveys had not yet been conceived. As instrumentation improved through the latter half of the century, the picture began to sharpen. The Shapley concentration was not a single galaxy cluster. It was a supercluster, a collection of galaxy clusters gravitationally organized into a structure of higher order. Modern surveys have resolved more than 8,000 individually catalogued galaxies within it, organized into dozens of major clusters. The central cluster alone, designated Abell 3558, carries a mass comparable to the most extreme structures found anywhere in the local universe. the total estimated mass of the Shapley concentration, accounting for the dark matter that constitutes the overwhelming majority of all cosmic mass, reaches figures on the order of 10,000 to 100,000 trillion times the mass of our Sun. Numbers at that scale cease to be useful in comparison with any human reference. The only meaningful scale is cosmic. Early studies generated wildly contradictory estimates of how strongly Shapley's gravity was actually influencing our motion. Some calculations suggested a modest contribution. Others concluded it was the controlling factor. The disagreement persisted through the 1990s and well into the 2000s because of exactly the same measurement challenges that had inflated the great attractor's numbers. Mapping a structure 650 million light-years away, with sufficient precision to calculate its gravitational pull on our local neighborhood is genuinely difficult, and uncertainties multiply at every step of the calculation. What became progressively clearer, especially after the great attractor's mass was slashed by 90% in 2005, was that Shapley had to be responsible for a substantial fraction of our peculiar velocity. The mathematics demanded it. Something had to account for the 56% the great attractor could not explain. The giant behind the curtain had been present all along, recorded by a brilliant astronomer in 1930, and only now beginning to receive the credit it had always deserved. But to fully grasp the scale of our cosmic surroundings, the story required one further revolution, and it came not from measuring where things are, but from tracking where they are going. In 2014, a paper published in the journal Nature introduced a fundamentally new way of thinking about our address in the universe. The research team, led by astronomer Brent Tully at the University of Hawaii, and including Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, was not simply constructing a larger map of galaxy positions. They were mapping where galaxies are moving. The distinction is essential. Knowing only the positions of objects tells you what a structure looks like. Knowing the velocities as well tells you what gravitational forces are shaping it. A galaxy is not a static point in space. It is a location on a trajectory, drifting toward regions of higher mass density and away from regions of lower density. If you can measure thousands of those trajectories simultaneously, you can trace the underlying gravitational architecture that drives them, the way you can deduce the contours of a river channel by watching the direction and speed of the water flowing through it. The team applied a technique called peculiar velocity mapping to thousands of galaxies, out to roughly 500 million light-years. They calculated the deviation of each galaxy's velocity from what pure cosmic expansion would produce. That deviation reveals local gravitational influence at work. A galaxy moving toward you faster than expansion predicts is being pulled in your direction by some nearby mass. A galaxy moving slower than expected is being pulled the other way. From these thousands of individual measurements, the team assembled a three-dimensional flow field, a map of the direction and speed at which every sampled galaxy was moving. They then searched for the boundaries of that flow. Where did galaxies on one side move toward a different gravitational center than galaxies on the other side? Those dividing lines, comparable to watershed boundaries separating river drainage basins, defined the outer edges of superclusters. What they found was a structure 520 million light-years across, encompassing approximately 100,000 galaxies with a total gravitating mass estimated at 100,000 trillion solar masses. They named it Laniakea. The word is Hawaiian, drawn from a traditional creation, chant, and it means immense heaven or immeasurable heaven. The name was contributed by a Hawaiian language expert named Nawa Napoleon, and it is apt. The thing it names defies ordinary spatial imagination. Within Laniakea, every galaxy flows toward a single region, the great attractor at the structure's center. From the far side of this 500 million light-year expanse, galaxies are drawn steadily inward. Our own galaxy, our entire local neighborhood, is caught in that flow, carried along like everything else toward the central concentration. The visualization accompanying the paper became one of the most widely viewed astronomy videos in the history of the Internet. It displayed for the first time what our cosmic watershed actually looks like from outside. A vast, irregularly shaped cloud of flowing matter with great filaments curling inward toward a central point of convergence. It was the most detailed map of our cosmic home ever assembled. And within months, astronomers had begun asking whether Laniakea itself was the full story. The Milky Way does not occupy the center of Laniakea. It sits near the outer boundary, in a region of the supercluster's extent that is relatively sparse and underpopulated compared to the dense interior. To borrow a human-scale comparison, if Laniakea were a sprawling metropolitan region, our galaxy would be a modest town on the remote outskirts, nowhere near the city center, and not even close. That peripheral position matters for what follows. All the galaxies within Laniakea, regardless of where they are located within the structure, flow toward the great attractor at its heart. The flow lines mapped by Tully's team show this convergence unmistakably. Motion from every direction pointing inward, like tributaries joining a central river. Our galaxy is part of that inflow, swept along by the same gravitational current that pulls everything in Laniakea toward the Norma cluster region. But Laniakea is not gravitationally bound. This is a critical distinction, confirmed by the same data that defined the supercluster in the first place. A gravitationally bound structure is one in which the mutual gravity of its members is strong enough to override cosmic expansion and ultimately draw everything together. Galaxy clusters are bound. Galaxy groups are bound. Our local group, which includes the Milky Way and Andromeda and dozens of smaller companions, is gravitationally bound. These smaller structures will remain cohesive and eventually merge. Laniakea as a whole will not. The universe's expansion is pulling the structure apart faster than the gravity within it can hold it together. Laniakea is defined by a shared flow pattern in this particular cosmic moment, but it is not a permanent object. Over billions of years, its outer regions will drift away. The name remains fitting regardless. The immense heaven is real, even if it is transient on cosmic timescales. What makes this chapter end on a genuinely unsettling note is what a new generation of surveys began to reveal in 2024. A team working with the Cosmic Flows 4 catalog, a database containing more than 56,000 measured galaxy distances, published a fresh analysis of gravitational flow basins. They found that the boundary of Laniakea may not be where the 2014 paper positioned it. The flows traced outward appeared to continue beyond Laniakea's defined edge. Galaxy motion that the 2014 model predicted should be heading toward some other attractor was instead still pointing in the same general direction. The implication was striking. Laniakea might itself be embedded inside a larger basin of attraction centered on the Shapley concentration. If that reading is correct, and the team assessed the probability at 60%, then our cosmic address is not Laniakea. Laniakea is a subdivision. The actual basin we inhabit could be 10 times larger in volume, with the Shapley concentration at its gravitational anchor. The immense heaven turns out to be the front yard of something even more immense, and that something, as we are about to see, is itself only part of the full picture. Because while astronomers were charting what pulls us forward, a separate discovery was being made about what drives us from behind. Everything uncovered so far pointed in one direction: pull. Dense clusters hauling at our galaxy through the dark. The Great Attractor, the Shapley supercluster, a gravitational landscape dominated by enormous overdensities, demanding that matter fall toward them. But the numbers consistently refused to close. Even after accounting for the combined mass of the Great Attractor and Shapley together, the full peculiar velocity of our galaxy could not be explained. Researchers kept working through the calculations and arriving at the same uncomfortable conclusion. Something else was contributing, something that had not yet been mapped. The answer arrived in January 2017 from the same team that had named Laniakea. Yehuda Hoffman, Daniel Pomerade, Brent Tully, and Hélène Courtois published a paper in Nature Astronomy, revealing a vast supervoid in the direction opposite to Shapley. They named it the dipole repeller. Here is what makes this counterintuitive. Voids do not push. There is no mechanism in standard physics by which empty space generates an outward force. What actually happens is subtler, and in some ways more unsettling. Imagine standing on a hillside that descends steeply in one direction and gently in another. You roll toward the steep descent. Viewed from your perspective, the gentle slope behind you appears to be propelling you away from it. It is not. It simply exerts less gravitational attraction than the steep side. The imbalance between the two slopes is what moves you. That is exactly the dipole repeller. A region of space so empty, so deficient in mass, that everything surrounding it accelerates away from it relative to what those objects would do in a perfectly uniform universe. The void stretches across more than 1 billion light-years. To give that scale a concrete shape, placed beside Laniakea, it would be nearly twice as wide as our entire home supercluster. Within that billion light-year expanse, there are essentially no galaxies. The cosmic web, which elsewhere threads the universe with filaments, nodes, and clusters, simply falls silent. Matter followed the attractors long ago, draining away from this region like water retreating from a dry plateau, leaving behind an emptiness so complete that astronomers can barely find objects to catalog within it. What confirmed all of this was the velocity flow field. Tully's team used galaxy motion surveys to reconstruct the gravitational landscape in 3 dimensions. When they removed the Hubble flow, what remained was a picture of every galaxy in our neighborhood, being simultaneously pushed away from one void and pulled toward one supercluster. 2 forces, 1 coherent motion. This result carried an immediate and unexpected consequence. The dipole repeller and the Shapley concentration turned out to contribute approximately equally to our galaxy's peculiar velocity, roughly 50% each. The Great Attractor, the structure that launched this entire investigation, was already a lesser player than Shapley. Now Shapley itself was sharing the stage with an absence of matter rather than a presence of it. The void proved to be exactly as powerful as the mountain. For the first time, the complete picture of our motion through the cosmos was beginning to cohere. A push from behind, a pull from ahead, a gravitational landscape sculpted by both what exists and what does not. But here is what nobody had fully accounted for yet. how do we actually measure all of this? What is the instrument that makes our velocity undeniable? The answer has been present since the Big Bang itself, and it covers the entire sky in every direction at once. Think of the universe as terrain. Dense galaxy clusters are the valleys, low points in the gravitational landscape where matter pools and flows accelerate. Vast supervoids are the high plateaus, regions so underdense that everything in their vicinity rolls away toward denser ground. Galaxies, clusters, superclusters, and our entire local group are water on this terrain, flowing along contours that have been shaping themselves since the first moments of existence. Now, consider where our galaxy sits within that landscape. Ahead of us, approximately 650 million light-years away in the direction of Centaurus, lies the Shapley supercluster. It is the deepest gravitational basin in our local universe. Thousands of galaxies crowded into a region of space so dense that it bends the flow field of everything within its reach. Its total gravitating mass, once dark matter is included, may approach 10 quadrillion times the mass of our Sun. Behind us, 2 billion light-years away, lies the dipole repeller, an expanse of near-nothingness stretching over a billion light-years across. No significant clusters, no major filaments, just the faint background scatter of matter left behind when everything else drained toward denser regions long ago. Together, these two structures explain something astronomers struggled with for decades. The Great Attractor region, which dominated this story for 30 years, actually accounts for only 44% of our galaxy's peculiar velocity. Shapley contributes more. The dipole repeller contributes as much as Shapley. Add the two together and the equations finally balance. This is a confirmed result. The 2017 paper by Hoffman, Pomerade, Tully, and Courtois established it through three-dimensional velocity field reconstruction drawing on observations of thousands of galaxies. It is among the most thoroughly verified findings in large-scale structure cosmology. What it means in practical terms is this. Our galaxy is not simply being attracted by something. It is being channeled, like water flowing through terrain shaped by both peaks and valleys. Our motion is the product of simultaneous forces drawing from one side and releasing from the other. You cannot understand why we move by studying only the attractors. The voids carry equal weight. There is something philosophically significant in this. For most of the history of observational cosmology, the discipline was organized around finding things: galaxies, clusters, superclusters, structures. The breakthrough that finally explained our motion came from mapping nothing, from recognizing that an absence of galaxies across a billion light-years was itself a gravitational object capable of reshaping the universe's entire flow field. The dipole repeller was invisible under the old framework. You cannot photograph emptiness. You cannot catalog voids the way you catalog clusters. What revealed it was the behavior of matter in its vicinity, the way galaxies nearby tilted slightly away, like compass needles deflecting from a field they cannot directly perceive. Both sides of the equation are now known. The pull, the push, the complete gravitational landscape within which our galaxy has been traveling for billions of years. But there remains a separate question, a deeper one. How fast are we actually moving through all of this? The attractors and repellers explain the direction. What measures the speed with certainty? The answer requires turning away from galaxies entirely and attending to the oldest light in the universe. In 1965, two radio engineers named Arno Penzias and Robert Wilson were attempting to eliminate interference from a communications antenna in New Jersey. No matter what they tried, a faint hiss persisted. It arrived from every direction in equal measure. They ran through every possible explanation. They even removed bird droppings from the inside of the antenna dish, suspecting contamination. The signal refused to disappear. What they had accidentally detected was the cosmic microwave background. The eye thermal afterglow of the Big Bang itself, still saturating every cubic centimeter of space, cooled over 13.8 billion years to just 2.7 degrees above absolute zero. The oldest light in the universe, printed onto the sky in every direction simultaneously. Initially, it appeared perfectly uniform. The temperature seemed identical in every direction to extraordinary precision. Then, in 1966, cosmologist Dennis Sciama noted that it could not be truly uniform. If we are in motion, the background radiation ahead of us should appear marginally hotter and the background behind us marginally cooler, a consequence of the Doppler effect, the same physics that makes an approaching siren sound higher-pitched and a receding one lower. Measurements confirmed this almost immediately. The cosmic microwave background is not perfectly uniform. One hemisphere of the sky is warmer than the other by approximately 0.003 of a single degree. That difference is real, consistent, and confirmed by every major satellite mission over the past 4 decades. The COBE satellite established it. The Wilkinson Microwave Anisotropy Probe refined it. The Planck satellite measured it to extraordinary precision in 2018. Our solar system moves at approximately 370 kilometers per second relative to the cosmic microwave background. That translates to roughly 828,000 miles per hour. Consider that figure carefully. A direct, absolute measurement of our speed through the universe, derived from a temperature difference of 0.003 of a degree in the oldest radiation we can observe. This is not a model. It is not an estimate extrapolated from galaxy catalogs or distance measurements. It is a direct observation. But there is an important nuance. That figure of 370 kilometers per second describes the motion of our solar system. Our galaxy as a whole moves faster at approximately 627 kilometers per second relative to the cosmic microwave background. Once the orbital speed of our solar system around the galactic center is properly factored out. The difference between those two numbers, roughly 260 kilometers per second, represents the accumulated motions of our solar system around the galaxy and the galaxy within the local group. At 627 kilometers per second, that translates to over 1,300,000 miles per hour. This is the peculiar velocity of a volume of space roughly 1,000,000 light-years across, all of it moving together toward the Great Attractor and Shapley like a drifting continent. And this measurement raises a puzzle that no one has yet satisfactorily resolved. When astronomers count radio galaxies distributed across enormous volumes of space, they detect a pattern in the sky that should match the cosmic microwave background dipole in both direction and magnitude. It does not match. Multiple independent surveys find the radio dipole running 2 to 4 times larger than the cosmic microwave background dipole would predict. This discrepancy has been confirmed by at least 4 separate datasets as of 2025, and nobody has produced a compelling explanation for it. The speedometer is functioning. The reading is unambiguous. What that reading might imply about the largest scales of the universe is an entirely different matter. Now it is time to add everything together. Each layer of motion described here is real. Each is confirmed by independent measurement. Each operates simultaneously, right now, on every object resting on this planet. When stacked together, the total is a number so large that the mind struggles to find any adequate comparison. Earth rotates at roughly 1,040 miles per hour at the equator. You feel nothing. Earth orbits our star at approximately 67,000 miles per hour. It covers about 1.6 million miles in a single day. In the time it takes to speak a single sentence aloud, you have traveled nearly 12,000 miles along the orbital arc. You feel nothing. Our solar system circles the center of the Milky Way at somewhere between 496,000 and 560,000 miles per hour. One complete circuit takes roughly 220 million years. The last time our solar system occupied this exact position in its galactic orbit, there were no dinosaurs on Earth, no mammals, no complex animals of any kind. We have completed approximately 20 of these orbits in Earth's entire existence. You feel nothing. Our galaxy moves through the local group. The local group falls toward the Virgo cluster. All of that contributes roughly 260,000 additional miles per hour when measured against the cosmic microwave background. And then there is the peculiar velocity of our entire cosmic neighborhood. More than 1,300,000 miles per hour, channeled simultaneously by the dipole repeller pushing from behind and the Shapley supercluster pulling from ahead, a flow encompassing millions of light-years of space all moving together. Add every layer. Earth is currently traveling at well over 1.9 million miles per hour through the universe. Not 1 million, not 500,000. 1.9 million miles per hour. That is approximately 2,000 times faster than a rifle bullet in flight. You feel none of it. The reason is, among the most elegant facts in all of physics, there is no friction in space. There is no medium to resist against. Every inertial reference frame is equally valid. No experiment performed inside a smoothly moving environment can detect that movement from within. We are passengers aboard a vessel that has never decelerated, never altered the conditions at its surface, never delivered any physical signal to our bodies that anything out of the ordinary is happening. We are, to use the phrase with precision, fish who have never seen water. The medium through which we travel is space-time itself, and the only evidence of our velocity is encoded in a temperature difference of 0.003 of a degree on one side of the sky. This is not an abstraction. It is the physical reality of every human being who has ever lived. The ancient astronomers who charted the stars, the navigators who steered by them, the philosophers who disputed whether Earth moved at all. Every one of them was tearing through the cosmos at nearly 2 million miles per hour without any awareness of it. But as extraordinary as this total is, the story does not stop here. Because not everyone agreed that this motion was what it appeared to be. Some astronomers examined all of this data and posed a different question entirely. What if the numbers themselves rested on a mistake? Science is a mechanism for exposing errors. Sometimes the error lives in the theory, sometimes in the observation, and sometimes in the mathematics linking the two. When the Seven Samurai published their findings in 1987, they had accomplished something technically formidable. They had measured the peculiar velocities of elliptical galaxies by comparing observed properties to the fundamental plane, a relationship linking galaxy size, luminosity, and internal velocity dispersion. It was careful work. It was also work built on a chain of assumptions, each introducing a small uncertainty, each uncertainty compounding against the next. The problem that would shadow the field for 2 decades already had a name. It was the Malmquist bias. Here is how it operates. When you observe galaxies at increasing distance, you can only detect the brightest members of each population. The faint, dim objects that make up the bulk of any distant sample fall below the sensitivity threshold of your instruments. This means that surveys at large distances are systematically skewed toward intrinsically luminous objects. If you then use apparent brightness to infer distance, as the fundamental plane method effectively does, that skew introduces a systematic error. Distant galaxy populations appear slightly closer than they actually are. Nearby populations appear to have systematically elevated velocities. The resulting signal, when the bias is not corrected for, looks exactly like coherent gravitational streaming toward a central attractor. It is an artifact that mimics a physical phenomenon with convincing precision. This was not a peripheral worry. A sequence of papers through the 1990s and early 2000s scrutinized the great attractor evidence and concluded that Malmquist bias had inflated the original mass estimates by a large factor. The 2005 clusters in the zone of avoidance survey reduced the great attractor's estimated mass by roughly 90%. Let that register properly. For nearly 2 decades, the standard description of our cosmic neighborhood featured a structure 10 times more massive than it actually is. Every popular article, every documentary, every astronomy lecture discussing the great attractor was describing something that did not exist in the form being presented. The confirmed picture as it stands today is this. The Norma cluster at the heart of the great attractor zone is real and massive. The streaming motion toward it is real. Our galaxy's peculiar velocity is real. What was wrong was the inferred mass, and consequently the assumption that this one structure could account for our motion on its own. The skeptical challenge extends further than mass estimates alone. Early peculiar velocity surveys relied on galaxy distances that carried uncertainties of 15 to 20%. That sounds manageable until you recognize that the signal being measured, the coherent streaming motion, was itself only a few percent deviation from the Hubble flow. A 15% uncertainty in the measuring instrument means the quantity being measured is effectively drowned in noise. Some researchers in the early 2000s argued that statistical artifacts in the distance data could produce apparent streaming motions with no physical basis whatsoever. On that reading, the data was not measuring the universe. It was measuring the limits of its own precision. The mainstream community responded by constructing better surveys, using larger samples, incorporating additional distance indicators, and building 3-dimensional flow maps instead of 1-dimensional velocity plots. They answered the critics with volume of evidence, and the motion held up. But the skeptical impulse was correct about one essential thing. Some of the most dramatic claims in this field, those that generated the largest headlines, would eventually unravel under sustained scrutiny. What follows is the most contentious discovery in modern cosmology. In 2008, a physicist named Alexander Kashlinsky sat down to write a paper he understood would generate controversy. Kashlinsky was based at the Goddard Space Flight Center, and he had spent years refining a technique for extracting a faint signal from the cosmic microwave background. The method exploited a phenomenon called the kinematic Sunyaev-Zeldovich effect. When background radiation passes through a galaxy cluster, the hot gas within the cluster scatters a fraction of those photons. If the cluster is moving toward us, the scattered photons are slightly blue-shifted. If it is moving away, they are slightly red-shifted. The effect is extraordinarily weak, less than 1/10 the amplitude of the cluster's thermal emission. But if you study hundreds of clusters simultaneously and average the signal with care, the noise cancels out and the motion component survives. Kashlinsky and his collaborators examined approximately 700 galaxy clusters using data from the Wilkinson microwave anisotropy probe. What they found was this: all 700 clusters were moving coherently in the same direction. The flow persisted across every distance they could probe. The clusters were not dispersing randomly as standard models predicted. They were streaming as an organized group toward a specific point in the sky. The velocity was close to 2 million miles per hour. The flow extended to at least 2.5 billion light-years. Kashlinsky named it dark flow. The designation would persist, and the debate around it would not resolve for years. The word dark here carries none of its usual cosmological associations with dark matter or dark energy. It means invisible, unaccounted for, a flow with no identifiable cause anywhere within the observable universe. Kashlinsky told reporters that his team had not been searching for this signal and found no way to make it disappear regardless of how they interrogated the data. A follow-up study 2 years later expanded the cluster catalog to roughly 1,400 objects. The signal held. The flow maintained approximately the same velocity out to distances twice those in the original detection. The direction pointed toward a broad region of sky between the constellations Centaurus and Vela. If dark flow is real, it ranks among the most significant observational discoveries in the history of cosmology. Standard cosmological models predict that, on scales larger than a few hundred million light-years, the universe should appear statistically identical in all directions. Any bulk flows should average out. No preferred direction should exist. A coherent motion extending across 2.5 billion light-years violates this prediction absolutely. And the only mechanism capable of generating such a flow would be extraordinary. To exert gravitational pull across distances that large, potentially spanning the entire observable universe, if the signal truly extends that far, there would need to be structures our instruments cannot observe because they lie beyond the cosmic horizon, beyond the edge of everything accessible to us. Kashlinsky's team proposed that dark flow might represent the gravitational signature of massive structures that formed during or before the period of cosmic inflation. Structures that now occupy space beyond the boundary from which light has had time to reach us. In other words, evidence for something beyond our universe. That interpretation was not left unchallenged. To understand why dark flow triggered a crisis in theoretical cosmology, you need to understand which foundational principle it threatened. The cosmological principle is one of the bedrock assumptions of the entire modern cosmological framework. It states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means the same at every location. Isotropic means the same in every direction. No special place exists. No preferred direction exists. Matter is distributed uniformly across the cosmos on average, and the expansion of space proceeds identically everywhere. This principle is not merely a convenient theoretical preference. It is what makes the standard cosmological model tractable. Without it, the equations governing the universe's evolution become vastly more complicated, potentially insoluble without information about initial conditions that lie beyond our reach. The cosmological principle is a working assumption that has been tested repeatedly and has held up well within its applicable range. Dark flow, if genuine, shatters it entirely. Coherent motion of galaxy clusters across 2.5 billion light-years implies a preferred direction in a cosmos that foundational theory insists has none. Something is gravitationally pulling on matter from a distance so vast that the source cannot lie within our observable horizon. Standard structure formation, the gravity of galaxies and clusters accumulating over billions of years, cannot produce a bulk flow that coherent across that spatial scale. The theoretical upper limit for a gravitationally induced bulk flow of this kind, within standard models, is far smaller in both velocity and extent. The only physical mechanism consistent with what Kashlinsky observed is something that originated before or during inflation and now inhabits space beyond the boundary from which light can reach us. The universe we can observe, the sphere of space roughly 93 billion light-years across, is not the entire universe. Standard inflationary models predict that the full universe extends many orders of magnitude beyond that boundary. If matter beyond our horizon is not uniformly distributed, it would exert gravitational forces on our side of that boundary, forces we might detect as a bulk flow precisely like the one Kashlinsky claimed to have measured. The implications are profound. If structures beyond our horizon are tugging at us, those structures could be regions of the universe that underwent different evolutionary histories during or after inflation. In some theoretical frameworks, inflation generates a universe of distinct domains, each with its own local physics and initial conditions. Neighboring domains, if close enough to our horizon, could exert gravitational tidal forces producing observable effects. Under this interpretation, dark flow would represent the first observational evidence of cosmological structure beyond the known universe's edge. Kashlinsky was careful to frame this precisely. He reported the observation clearly and presented the multiverse interpretation as one possibility among several, not as a conclusion. The confirmed claim was the bulk flow itself. The theoretical implications were explicitly speculative. But the astronomical community watched closely. The kinematic Sunyaev-Zeldovich method was sound in principle. The cluster sample was substantial. The direction and magnitude appeared consistent across independent cuts of the data. And then the most precise instrument ever aimed at the microwave background turned toward the same clusters. Its findings did not align. The Planck satellite, launched in 2009, spent 4 years mapping the cosmic microwave background with a level of precision no previous instrument had approached. Its detectors could resolve temperature differences of millionths of a degree. Its angular resolution exceeded that of any prior mission. If any signal associated with dark flow were real and anywhere near the amplitude Kashlinsky reported, Planck would have found it. In 2013, the Planck collaboration published its reconstruction of galaxy cluster velocities using the same kinematic Sunyaev-Zeldovich method Kashlinsky had employed. Their conclusion was restrained but clear. They found no statistically significant dark flow at the amplitude the 2008 paper had claimed. The velocity signal in their data was consistent with zero. This was a serious challenge. The kinematic Sunyaev-Zeldovich effect is among the most technically demanding signals to extract from microwave background data. The thermal emission from cluster gas is many times stronger than the kinematic component. Isolating the latter requires precise knowledge of each cluster's temperature structure, detailed modeling of foreground contamination, and rigorous statistical treatment of a sample that inevitably carries measurement scatter. Critics of Kashlinsky's analysis identified multiple potential sources of systematic error. The original cluster sample was drawn from X-ray catalogs carrying their own selection biases. The signal-to-noise ratio for any individual cluster was far below the threshold of detection. The entire claimed detection rested on statistical averaging. Small errors in the foreground model, the kind that accumulate invisibly across a large-scale analysis, could generate apparent correlations indistinguishable from coherent motion. Fernando Atrio Barandella, one of Kashlinsky's close collaborators, published a reanalysis in 2015 arguing that the Planck data, when processed with different assumptions, was actually consistent with the original Wilkinson probe findings. The debate became intensely technical, with competing teams disputing the methodology of each other's analyses at a level of granularity accessible only to specialists in the field. Follow-up studies produced genuinely contradictory results. Some confirmed a bulk flow in approximately the expected direction. Others found signals statistically consistent with zero. Others found signals smaller than Kashlinsky's original estimate, but larger than Planck's upper bound. The field divided along methodological lines, with researchers unable to agree on how to handle systematic errors before they could agree on what the data said. This is science working at its frontier. That description is sometimes deployed as a soft way of saying we do not know. Here, it means something more specific. The measurement in question sits so close to the noise floor of current instruments that distinguishing a genuine signal from a systematic artifact requires assumptions, and the outcome depends heavily on which assumptions are made. What is established? Bulk flows on scales up to a few 100 million light-years are real and robustly confirmed. What is uncertain? Whether any flow extends coherently to 2.5 billion light-years. What remains genuinely unknown? Whether the signal Kashlinsky measured reflects physical reality or accumulated systematic error. As of 2026, the dark flow question has not been settled. The Euclid Space Telescope, launched in 2023, is expected to provide a definitive answer using an independent method. But while that debate continued, a wholly different kind of cosmic discovery arrived from a direction no one anticipated. A sphere of galaxies, 1 billion light-years across, sitting in our immediate cosmic surroundings. In September 2023, Brent Tully sat down to write a paper about a discovery so unlikely that his team spent months verifying it before submitting. Using the Cosmic Flows 4 catalog, a compilation of distance measurements for more than 56,000 galaxies assembled over years of work with the Hubble Space Telescope and multiple other observatories. The team had found something in the data that no one had seen before. A spherical shell of galaxies 1 billion light-years in diameter, located 820 million light-years from the Milky Way. They named it Ho'olelana, a word drawn from the Kumulipo, the Hawaiian creation chant, meaning stirrings of awakening. The structure is remarkable on several counts. First, its sheer scale. 1 billion light-years across. Our entire home supercluster Laniakea spans 520 million light-years. Ho'olelana is nearly twice that size. Its shell contains the Sloan Great Wall, the CFA 2 Great Wall, and the Hercules Supercluster Complex. The Boötes supercluster sits at its geometric center. Inside the shell lies the Boötes void, one of the largest known empty regions in the observable universe. Second, its proposed nature. Thule's team believed they had identified the first individual baryon acoustic oscillation ever resolved as a distinct physical structure. A baryon acoustic oscillation is a fossilized sound wave. In the first 380,000 years after the Big Bang, the universe existed as a hot, dense plasma. Sound waves, pressure oscillations, propagated through that plasma at roughly 58% of the speed of light. When the universe cooled enough for hydrogen atoms to form and light to travel freely, those waves froze in place. They ceased propagating and left their imprint on the distribution of matter throughout all of space. The physical scale of a frozen baryon acoustic oscillation is fixed by the speed of sound in the early universe and the moment at which the plasma cooled. It corresponds to a characteristic separation distance of roughly 500 million light-years. When astronomers analyze the statistical distribution of galaxy pair separations across large surveys, they find a slight excess at this scale. That excess is the baryon acoustic oscillation signal, confirmed across hundreds of statistical analyses over more than 2 decades. But those are statistical patterns spread across millions of galaxies. Nobody expected to encounter one as a single identifiable sphere. Ho'olelana appears to be exactly that. The research team describes it as a probable identification, not a certainty. The structure's geometry is consistent with a baryon acoustic oscillation. Its diameter matches the predicted scale. Its shell contains the kind of overdensity expected from a frozen pressure wave. The team is confident enough to publish, but careful to note that a single structure cannot be definitively classified as a baryon acoustic oscillation without the statistical context of finding many such spheres. If the identification is correct, we live inside an echo of the Big Bang. And the implications for measuring the universe's rate of expansion were even more striking than the discovery itself. Baryon acoustic oscillations are one of cosmology's most powerful measurement tools, and for a straightforward reason. The physical scale of the frozen sound wave is set by well-understood early universe physics. It functions as a standard ruler, a length that can be predicted from first principles. If we observe that ruler in today's galaxy distribution and measure how large it appears on the sky, we can calculate the distance to that region of the universe. If we then measure its redshift, the extent to which the universe has expanded since that light was emitted, we can calculate the expansion rate. This is how baryon acoustic oscillations became one of the primary methods for measuring the Hubble constant, the number describing how fast the universe is currently expanding. The complication is that 2 fundamentally different measurement approaches have been producing different answers for over a decade. Measurements grounded in the cosmic microwave background and the standard cosmological model yield a value of approximately 67 kilometers per second per megaparsec. Direct measurements using nearby distance indicators, including Type 1a supernova and Cepheid variable stars, consistently return values around 73 kilometers per second per megaparsec. The gap between these 2 numbers is statistically significant. It persists across multiple independent datasets from multiple independent research teams. Cosmologists call it the Hubble tension. Then, Ho'olelana entered the picture. If the sphere is genuinely a baryon acoustic oscillation, its observed diameter provides an independent measurement of the Hubble constant. Tully's team performed that calculation. Their result, 76.9 kilometers per second per megaparsec. Not 67, not 73. Higher than both values currently in contention. This result is preliminary. It derives from a single structure, a sample of one, in a discipline where robust measurements demand many observations averaged together. The uncertainty range in Tully's calculation is wide enough to overlap with the higher end of existing estimates, though not with the cosmic microwave background value. It must be treated as a data point, not a verdict. But what it represents is this. If the universe is filled with fossilized acoustic shells and we are only now beginning to resolve individual ones because our surveys have finally grown large enough and precise enough to detect them, then each new identification deepens our understanding of how matter is distributed across the cosmos and how rapidly space is expanding. We live inside one of these shells. The Milky Way sits within Ho'olelana's volume, closer to the outer edge than to the center. When you look outward at the large-scale structure of our cosmic surroundings, some of what you are observing reflects the geometry of a pressure wave that traveled through the plasma of the newborn universe before a single star had ever ignited. The echo has surrounded us all along, and far beyond our neighborhood, at distances reaching 9 billion light-years, two structures have just been identified that should not exist under any known physics. They exceed the theoretical size limit by a wide margin, and they appear almost side by side in the sky. A graduate student found something that had no right to exist, and the field of cosmology has been struggling to accommodate it ever since. Alexia Lopez was completing her doctoral research at the University of Central Lancashire when she noticed a pattern in data from the Sloan Digital Sky Survey. She was tracing the way ancient quasar light accumulates chemical signatures as it crosses the universe. When that light passes through the gas halos surrounding galaxies and clusters, it picks up absorption features the way a traveler's clothing absorbs the sense of every place they pass through. By reading those signatures across tens of thousands of lines of sight, Lopez could chart the matter distributed between us and the most distant light sources in the observable sky. In 2021, she announced a result that stopped colleagues mid-conversation. The structure she had mapped was a vast, curving arc of galaxies and galaxy clusters stretching 3.3 billion light-years from end to end. It hung in the sky near the constellation Boötes, 9.2 billion light-years from Earth. The light that reveals it left its source before our planet had formed. The problem is this. According to the cosmological principle, and according to every major simulation astronomers have built to model cosmic structure formation, the largest coherent structure that gravity and expansion together should permit is roughly 1.2 billion light-years across. The giant arc is nearly 3 times that limit. When researchers first heard the announcement, the objections began almost immediately. Then Lopez returned to work. In January 2024, at the 243rd meeting of the American Astronomical Society, she announced a second discovery at almost exactly the same cosmic distance, only 12 angular degrees away from the giant arc in the sky. She named it the Big Ring. The Big Ring measures 1.3 billion light-years across. Its full circumference reaches 4 billion light-years. If it were somehow visible to the naked eye from Earth, its disk would span the width of 15 full moons, arranged side by side across the night sky. It occupies the same cosmic epoch as the giant arc. 2 enormous structures at the same distance, in the same region of the sky. The Big Ring carries an additional peculiarity. When Lopez's team analyzed its three-dimensional geometry, they found it is not a flat circle. It traces a corkscrew spiral through space, its plane oriented almost directly toward Earth, meaning we are observing it nearly face-on. Neither structure fits comfortably into any accepted physical explanation. Baryon acoustic oscillations carry a characteristic scale of roughly 500 million light-years. The Big Ring is more than twice that size, and its geometry is inconsistent with a sound wave remnant. Cosmic strings, topological defects left over from phase transitions in the early universe, have been proposed as a candidate mechanism. Physicist Roger Penrose's conformal cyclic cosmology raises the possibility that rings of this kind could be echoes from black hole collisions in a universe predating our own Big Bang. Oxford physicist Subir Sarkar stated plainly that the rings change the game entirely, representing nothing that chance would be expected to produce. Lopez has since identified an even larger outer arc partially encircling both structures. The picture keeps expanding, and what it is expanding into places one of the most fundamental pillars of modern cosmology under mounting pressure. The cosmological principle is not a minor working assumption. It is the foundation on which every cosmological model of the past century has been constructed. At its core, the principle asserts that the universe is homogeneous and isotropic on large enough scales. Homogeneous means uniform at every location. Isotropic means identical in every direction. Together, these conditions allow scientists to write equations describing the entire observable universe as a single coherent system. Without that assumption, the mathematics of cosmology as currently practiced would collapse. There would be no single Hubble constant, no uniform expansion rate, no universal description of dark energy. The principle has been validated repeatedly at moderate scales. Surveys of millions of galaxies show that the universe, averaged across volumes of several hundred million light-years, does appear statistically smooth. Dense filaments and voids cancel when you zoom out far enough. The question is, how far back is far enough? The theoretical upper limit for a coherent structure, the largest object that gravity and expansion together should be able to sustain before cosmic uniformity overwhelms local clustering, sits at around 1.2 billion light-years. This limit is a direct consequence of the cosmological principle. Structures larger than this are, in the formal language of the field, prohibited. The giant arc stretches 3.3 billion light-years. The Big Ring spans more than 1 billion light-years in diameter and 4 billion in circumference. The Ho'olelana bubble discovered in 2023 is 1 billion light-years wide. And in 2022, astronomers confirmed the giant gamma-ray burst ring, another circular structure measuring over 5 billion light-years across. Each individually constitutes an anomaly. Taken together, they form a pattern. Scientists are actively debating what that pattern means. One legitimate possibility is measurement error. These are subtle signals extracted from statistical analyses of millions of faint objects at cosmological distances. Systematic biases in the data could mimic coherent structure where none truly exists. This concern is genuine. The history of cosmology contains numerous phantom structures that dissolved when more precise data arrived. A second possibility, currently described by several researchers as a credible theoretical option, is that these are genuine physical structures whose existence requires physics beyond the current standard model. Cosmic strings are one candidate, theoretical, one-dimensional defects in space-time that would have formed during early universe phase transitions, analogous to cracks forming in ice as it freezes. A cosmic string could seed a ring-shaped galaxy distribution by gravitationally concentrating matter along its length. A third possibility, presented by Roger Penrose as a specific prediction of his conformal cyclic cosmology, is that large rings of this kind are Hawking points, imprints of black hole evaporation events from a preceding cosmic cycle. This remains speculative. The most unsettling possibility is this: the cosmological principle itself may hold only within a restricted range, and the universe at scales of several billion light-years may be genuinely inhomogeneous in ways the standard model cannot accommodate. For now, this remains an open scientific question rather than a confirmed crisis. But the accumulation of anomalies is accelerating, and the instruments probing the sky continue to improve. What changed in 2024 was not a single new structure. It was a new map of everything. At the close of 2024, a paper in Nature Astronomy quietly rewrote our cosmic address. The team was led by Aurelian Valade and included Yehuda Hoffman, Noam Liebeskind, and others who had spent years assembling the most detailed three-dimensional map of galaxy motion ever constructed. Their raw material was the Cosmic Flows 4 catalog, produced by R. Brent Tully's group at the University of Hawaii, which had painstakingly measured distances to 56,000 galaxies. With both distances and velocities in hand, the team could chart not only where galaxies are located, but which gravitational basins they are falling toward. The method is the same one that produced Laniakea in 2014, tracing cosmic watersheds. Just as every raindrop on a mountain eventually reaches one ocean or another, depending on which side of the watershed it falls on, every galaxy is falling into one gravitational basin or another. The boundaries separating those basins are the true edges of superclusters. When Valade's team drew those boundaries using the richer Cosmic Flows 4 data, the picture that emerged was startling. Laniakea, our home supercluster, the structure that encompasses our galaxy near its outer edge, and was itself a revelation when announced a decade ago, may be enclosed within something enormously larger. The data assigns a 60% probability to the interpretation that the Milky Way lies inside the gravitational basin of the Shapley concentration. If that interpretation holds, the Shapley basin would be 10 times the volume of Laniakea. Consider what that implies. A decade ago, Laniakea seemed like our home on the largest scale, 520 million light-years wide, 100,000 galaxies, a mass equivalent to 100,000 billion suns. It felt like the final layer of our address. It may be a district within a vastly larger city. Tully has described the universe as an immense web in which galaxies run along filaments and gather at nodes, with matter flowing within basins, the way rivers flow within watersheds. What the 2024 map revealed is that those basins extend much further than anyone had previously calculated. The Shapley concentration, already the most massive known concentration of matter, within 1 billion light-years, may be the gravitational anchor of a domain encompassing everything we have so far mapped and more beyond it. The paper also confirmed a finding about the 5 additional superclusters charted by a 2023 study from the same research group. Those superclusters, named Apus, Hercules, Lepus, Perseus Pisces, and Shapley, are all substantially larger than any theoretical simulation of standard cosmology predicts they should be. The researchers describe the discrepancy as an unresolved puzzle. Our cosmic address keeps growing. Each revision makes the previous version sound familiar, and then the next layer peels away to reveal something larger still. But there is another force sculpting our trajectory through this structure, and it does not originate from any attractor. It comes from behind us. To understand why we move, both sides of the gravitational equation must be understood. For decades, astronomers treated the Milky Way's peculiar velocity as a story, entirely about attraction. The great attractor was pulling. Then Shapley was pulling harder. The reasoning was gravitational throughout, and the assumption was that all the meaningful physics lay in the direction we were heading. The vast underdensities behind us were treated as inconsequential background scenery. The 2017 discovery of the dipole repeller began correcting that picture. A billion light-year-wide void in the approximate direction opposite Shapley, containing essentially no galaxies, was contributing as much to our motion as the combined pull of all the attractors. The physics was not anti-gravity. It was geometry. In a region where matter is nearly absent, the gravitational pull is weaker than the cosmic average. Relative to a uniform universe, that imbalance creates a slope that galaxies roll away from. We were not simply being pulled forward, we were being pushed from behind. But the identification in September 2017 of a second massive void, found by the same team in the direction associated with the cosmic microwave background's famous cold spot, suggested the repulsive landscape behind us was even more extensive than anyone had estimated. The cold spot has puzzled astronomers for many years. It is a region of the microwave background considerably cooler than its surroundings, an anomaly that has generated many proposed explanations. An extensive underdensity along the line of sight can produce cooling in the background radiation through the integrated Sachs-Wolf effect, in which photons lose energy as they traverse a low-density region. The cold spot repeller was identified as a void whose presence contributes to this cooling effect. What the 2023 analysis using cosmic flows for data revealed is something that fundamentally alters the scale of the picture. The dipole repeller and the cold spot repeller do not appear as two separate structures in the updated velocity maps. They appear as a single enormous entity, a combined underdensity so vast that it constitutes one entire side of the gravitational landscape defining our cosmic motion. We are positioned between two of the most extreme features in the local universe. On one side, the Shapley concentration, the most massive known matter overdensity within a billion light-years. On the other, a combined void system extending across a region large enough to dwarf entire superclusters. The repulsive side of our motion is structurally more significant than originally recognized. And yet, something stranger persists. When astronomers examine the largest accessible scales of the universe and measure the directional signature our motion ought to imprint on the background radio sky, the number they find is wrong. It is far larger than expected, and the discrepancy resists every attempt to explain it away. Here is a prediction that should be straightforward to verify. If our galaxy's motion through the cosmos is governed entirely by local gravitational forces, by the pull of Shapley, and the push of the combined void system, then that motion should leave a specific imprint in the distribution of the most distant objects in the sky. Radio galaxies and quasars lie scattered billions of light-years away, far beyond the structures influencing our local motion. If we count them across the full sky, the count should be very slightly elevated in the direction of our motion and slightly reduced in the opposite direction, because our velocity compresses wavelengths slightly in the forward direction and stretches them in the other. This effect is called the radio dipole. Its amplitude and direction should agree closely with the cosmic microwave background dipole because both are measuring the same underlying motion. They do not agree. Multiple independent surveys have found a radio dipole 2 to 4 times larger than the cosmic microwave background dipole predicts. The discrepancy has been identified in the NRAOVLA Sky Survey, in data from the Wide Field Infrared Survey, Explorer Satellite, and in the Rapid ASCAP Continuum Survey. The direction is approximately consistent with the microwave background dipole, but the amplitude is dramatically, stubbornly, persistently larger. In 2025, a team led by Dharma applied the most sophisticated available statistical corrections, accounting for every known source of bias and systematic error, and reanalyzed the data. The anomaly held. The excess dipole signal did not diminish to the predicted level regardless of how carefully the noise was stripped away. What could account for this? One possibility is that something genuinely intrinsic to the matter distribution at the very largest accessible scales is responsible. Perhaps the universe is not as homogeneous as the cosmological principle demands, even at distances of several billion light-years. The radio sources in these catalogs are not local objects whose positions reflect the same gravitational flows that pull on us. They are so distant that any intrinsic clustering would have to be immense to produce a signal at this level. A second possibility is that our motion is generating effects that exceed what standard models predict, for reasons not yet understood. A third possibility is systematic error at a level that has thus far resisted every correction attempt. As of 2026, this stands as one of cosmology's most acute unresolved tensions, alongside the Hubble tension and the structural challenge posed by the giant arc and the Big Ring. And then in 2024, the instrument designed to map dark energy across billions of light-years announced results that sent a shockwave through physics. For 25 years, the standard cosmological model has rested on a quiet assumption that the energy driving the accelerating expansion of the universe is constant. Einstein introduced the concept as a mathematical term in his field equations, a cosmological constant, a fixed energy density woven into the fabric of space-time itself. He later described it as his greatest blunder. But the universe turned out to need it after all. When supernova observations in 1998 revealed that the expansion was accelerating rather than decelerating as gravity should ensure, the cosmological constant returned as the simplest explanation for what the data was showing. Constant dark energy, eternal acceleration, a universe expanding forever into cold and empty darkness. In 2024, the Dark Energy Spectroscopic Instrument at Kitt Peak Observatory in Arizona released its first major results from a survey of 6 million galaxy redshifts. The instrument had been designed to measure the history of cosmic expansion with unprecedented precision, and the data it returned suggested that dark energy was not behaving like a constant. The signal was significant, but not yet conclusive. The community waited. In March 2025, the instrument released results based on nearly 15 million galaxies and quasars, combined with data from the cosmic microwave background, supernova surveys, and weak gravitational lensing observations. The evidence strengthened when all these independent datasets were analyzed together. The best fit to the combined data required dark energy that had evolved over time. Stronger in the past, weaker today, and still weakening. The standard cosmological constant model, which assumes that the ratio of dark energy's pressure to its density is precisely -1 and never changes, was rejected by the combined data at high confidence. In November 2025, a team at Yonsei University in South Korea published a corrected analysis of supernova observations in the monthly notices of the Royal Astronomical Society. Their conclusion was more direct still. The universe may have already stopped accelerating. The great cosmic expansion that everyone assumed would continue indefinitely may have entered a phase of deceleration sometime within the last few billion years. The implications spread through everything we thought we understood about our ultimate destination. If dark energy is genuinely weakening, the expansion that has been carrying the Shapley supercluster away from us faster than we can approach it may be losing its grip. The attractors are not necessarily receding forever. The gravitational architecture of the cosmos may be in the process of changing. And one physicist, working with all the new data assembled, went further than anyone else had ventured in 2025. He performed the calculation that most scientists had been carefully avoiding. He calculated when the universe would end. The idea that the universe might terminate in collapse fell out of scientific fashion 25 years ago. When the accelerating expansion was confirmed in 1998, it appeared to seal the cosmos's fate as cold eternity. Galaxies would drift ever further apart. Stars would exhaust themselves and go dark. Eventually, the universe would reach a state of maximum entropy. Its energy spread so thin that nothing could happen anywhere. The big freeze, the heat death, an endless silent dark. The big crunch, the scenario in which everything ultimately falls back toward a singularity, became a historical relic. The textbooks moved on. In autumn 2025, Cornell University physicist Hitoshi Murayama published a paper in the Journal of Cosmology and Astroparticle Physics titled The Lifespan of Our Universe. Murayama used the latest results from the Dark Energy Spectroscopic Instrument, the Dark Energy Survey, and a suite of complementary observations. He modeled dark energy as an ultralight particle called an axion, a well-motivated theoretical candidate that had been proposed decades earlier for unrelated reasons. When he fit the data, one conclusion emerged consistently regardless of how he adjusted the underlying assumptions. The cosmological constant is likely negative. A negative cosmological constant means the energy driving expansion is not merely weakening. It will eventually change sign. The expansion will decelerate, stop, and reverse into contraction. According to this calculation, the universe will continue expanding for another 11 billion years before reaching its maximum extent. Then it will begin to contract. The collapse will accelerate as gravity compounds on itself, and roughly 20 billion years after that turning point, everything will converge back toward a singularity. Total lifespan of the universe, approximately 33 billion years. The universe is currently 13.8 billion years old. That places us just under halfway through. Independent confirmation came in a separate paper by Shajib and collaborators, published in Physical Review D in September 2025. Their analysis of multiple dark energy datasets found that dark energy has decreased by approximately 10% over recent cosmic history, and they rejected the constant dark energy model at 99.6% confidence. The Big Crunch is no longer a discarded hypothesis. It is a scientifically motivated scenario supported by multiple independent lines of evidence. It is described as credible, though contested, and future observations from the Euclid Space Telescope and the Vera Rubin Observatory will sharpen or dissolve the signal in the years ahead. For this story, the implications cut deeply. We have spent many chapters calculating the speed at which we hurtle toward the Shapley supercluster, a destination so remote and the expansion so relentless that arrival seemed forever impossible. But if expansion is genuinely reversing, the picture of motion without destination begins to look different. Except for one complication, the timescales involved exceed the limits of meaningful imagination. And what happens to the journey long before the universe ends is stranger, quieter, and in some ways more haunting. We are moving toward the Shapley supercluster at over 600 kilometers per second. We have been doing so for billions of years. We will continue doing so for billions more. We will never arrive. This is the fundamental irony at the heart of our cosmic motion. Every attractor described in this story, the Great Attractor, the Shapley concentration, the entire basin of attraction that may enclose them both, represents a destination we perpetually approach and never reach. The reason is dark energy. Even in its weakened current form, the expansion of space continues to carry distant structures away from us. The Shapley supercluster lies 650 million light-years away. The galaxies at its core are receding from us at a velocity set by cosmic expansion, and while our peculiar velocity of 600 kilometers per second is substantial on a local scale, the recession velocity of Shapley is thousands of times larger. In the time it would take us to cover even a modest fraction of the distance toward Shapley, the structure itself would have retreated further still. To reach the Great Attractor region alone, traveling at our current peculiar velocity would take approximately 5 billion years. Our solar system will be unrecognizable long before that interval elapsed. And the Great Attractor itself would have moved. The motion is real. The velocity is real. The destination does not exist in any practical sense. There is no analogy in human experience for this condition. We move toward something that perpetually retreats. We accelerate toward an attractor that is simultaneously being carried away by the medium through which we travel. It is not that the destination is concealed or far away the way a horizon is far away yet reachable. It is that the destination is withdrawing at a rate our velocity can never overcome. Consider this image. Imagine running toward a shoreline painted on a canvas that is unrolling away from you. Your legs are moving. You are covering ground. But the canvas unrolls faster than you can run. You are always in motion. You are never arriving. Even in the scenario where dark energy ultimately reverses and the universe begins contracting, the timescales involved, 11 billion years before maximum expansion and then 20 billion more years of collapse, are so vast that no meaningful sense of arrival applies to anything we might call ourselves. The structures we flow toward will have merged, dispersed, or been transformed by processes we cannot predict. We are travelers on a journey with no terminus. Pure motion, pure becoming, a direction that points forever forward but never resolves into a destination. And yet something remarkable lives inside this fact. The entirety of the motions we have mapped, the nested velocities, the gravitational basins, the pushing voids and drawing superclusters, traces back to events that unfolded in the first fraction of a second of the universe's existence. The architecture of where we are going is a fossil record of where we came from. That realization deserves to be held with care, because it changes what this entire journey means. Consider everything assembled across the length of this account. At the smallest scale, Earth spins on its axis at over 1,000 miles per hour. That rotation sweeps us around our star at 67,000 miles per hour. The entire solar system wheels around the galactic center at nearly 500,000 miles per hour, completing one full orbit every 220 million years. The galaxy moves within the local group, which falls toward the Virgo cluster, which flows as part of Laniakea toward the Great Attractor, which is itself embedded in the larger gravitational domain of the Shapley concentration, which may flow within currents we have only begun to detect. Stack those speeds together, and you are traveling at roughly 2 million miles per hour through the universe. You feel nothing. The attractors and repellers shaping that motion are not random. They are direct descendants of density fluctuations that existed in the first 380,000 years after the Big Bang, when the universe was a hot plasma and pressure waves propagated through it at more than half the speed of light. Those waves froze in place when the universe cooled and became transparent. The pattern they imprinted, encoded in the distribution of galaxies visible across the sky today, is the map of where everything is going. We are driftwood on an ocean whose currents were carved by sound. This is confirmed by multiple independent observations. The cosmic microwave background, the distribution of galaxy clusters, the baryon acoustic oscillation signal in large-scale surveys, the peculiar velocity fields mapped by decades of painstaking measurement all converge on the same narrative. The forces moving us were set in motion before any star in the universe had begun to burn. The Ho'olilana bubble, a billion light-year spherical shell of galaxies found in 2023, is a physical remnant of one of those primordial sound waves, still legible in the arrangement of matter nearly 14 billion years later. We live inside a fossilized echo of the universe's first voice. Here is what makes all of this genuinely extraordinary. A creature that lives for 100 years on a world that completes one galactic orbit every 220 million years, on a fragment of rock near the outer edge of an unremarkable galaxy, has managed to measure the curvature of the universe's gravitational landscape across hundreds of millions of light years, has located the voids pushing from behind, has traced the drainage basins shaping the flow of 100,000 galaxies, has followed the origin of that entire architecture back to acoustic oscillations in a plasma that has not existed for nearly 14 billion years. That achievement does not require manufactured awe. It is simply what it is, one of the most audacious acts of understanding in the entire history of this planet. We do not know where we are going. The destination, as this story has established, does not exist in any reachable form. But, for the first time, we understand in genuine depth why we are moving, what is moving us, and how far back the cause of our motion reaches into the universe's past. That understanding is not the conclusion of this story. The most significant anomalies remain unresolved. The dipole discrepancy has no accepted explanation. The giant arc and the big ring stand in open defiance of the standard model. The nature of dark energy is being actively disputed at the highest levels of the field. We remain inside the mystery. We have simply mapped more of its contours than anyone before us. And now, one final time, let us place everything together. You are never at rest. Right now, the ground beneath you is rotating at over 1,000 miles per hour, sweeping you through the arc of a single day. At the same time, This entire planet is racing through its orbit around our star at 67,000 miles per hour. In the course of a single day, Earth covers 1.5 million miles along that orbital path. You will never occupy this exact position in space again. But that orbital speed, which exceeds any velocity ever achieved by a human being through personal effort, barely registers in the full accounting. Our solar system is circling the center of the Milky Way at nearly 500,000 miles per hour. One complete revolution takes 220 million years. The last time our solar system held this position in its galactic orbit, the Triassic was opening on Earth, and the ancestors of every dinosaur had not yet appeared. We have completed roughly 20 such revolutions since our planet formed. Each one a silent, unfelt passage through a galaxy we have never once seen from the outside. Stack those speeds, and we are already moving at more than 500,000 miles per hour. But we are not finished. The Milky Way, together with Andromeda and the dozens of smaller galaxies forming our local group, is falling toward the Virgo cluster. The local group as a whole carries a peculiar velocity exceeding 1,300,000 miles per hour relative to the cosmic microwave background. That is the combined pull of the Great Attractor region and the Shapley supercluster together with the push of the merged void system behind us. The I dipole repeller and cold spot repeller, forming the largest underdensity in the known local universe, layer every motion together. The final total exceeds 1.9 million miles per hour. This is what science has assembled across decades of effort spanning the full breadth of observational astronomy. The seven samurai who noticed in 1986 that something was pulling galaxies in the wrong direction. Brent Tully, Helene Courtois, Yehuda Hoffman, and Daniel Pomered, who in 2014 drew the boundaries of Laniakea and gave our home in the universe a name worthy of it. The team that identified the dipole repeller in 2017, finally explaining why the attractors alone never balanced the equations. Tully and his collaborators again in 2023, recognizing in Ho'olelana the first physical remnant of a Big Bang sound wave. Alexia Lopez, the doctoral student who discovered structures 3 times larger than the universe should permit. Not once, but twice, and then found something even larger encircling both. The universe these researchers have revealed is not the one anyone expected to find. It is a surging current of galactic motion, driven by forces set in motion before our star existed, flowing toward destinations that retreat as we approach them, structured by echoes of pressure waves from an era when the universe was smaller than the smallest star. Dark energy appears to be fading. The expansion that seemed permanent may already be slowing. A physicist at Cornell has calculated that the universe will reach its maximum extent in 11 billion years, and then contract over 20 billion more toward an end. If that calculation proves correct, we are traveling not only through space but through a finite cosmic lifespan, and we happen to exist near its midpoint. The motion will persist long after every living thing on this planet is gone. The galaxies of Laniakea will keep flowing toward the Great Attractor. The Great Attractor's basin will keep flowing toward Shapley. Shapley itself will keep flowing within currents we have only begun to trace. We will not be present to observe any of it. But the fact that we looked upward from this small spinning world and measured the shape of all that motion using instruments no larger than a building, and traced it all the way back to the first sound ever produced in the universe, is something that will endure in the record of what life on Earth once achieved. We were never still. We are still moving. We are only now beginning to understand what that means. And perhaps that understanding, this hard-won map drawn across centuries of looking outward, is itself the most remarkable thing our brief presence in the cosmos has produced. The universe does not know we are here. But we know where we are going, and for a creature that lives 100 years on a journey measured in billions, that knowledge is not a small thing. It is everything.